Okay, uh, today we'll start with the third application, electric field intensity due to uniform charge, thin, this is thin spherical shell. Okay, now we have a spherical shell. Spherical shell means you are what? You are having a, see here, this is your spherical shell. Okay, this is a sphere. Sphere means you are what? That is not a circle, it is your tennis ball. Imagine your tennis ball, and on the tennis ball, inside the tennis ball, it is hollow. It is hollow, and the charge is distributed uniformly on this sphere, right? This is called thin spherical shell. Now we wish to find the electric field due to these positively charged positive charge which is uniformly distributed on the shell, outside the shell, on the shell, and inside the shell. Okay, that means outside the tennis ball, on the tennis ball, and inside the tennis ball. These are the three cases which we will take up here. Now we will take here point P where electric field is to be calculated, and through point P we will make a Gaussian surface, and that Gaussian surface will be also your what? That will be also your sphere. Now we will take your this this is having the radius, see here, this is O is the center, R is your its, okay, this R is the radius of your spherical shell. Okay, now the first case is here at a point P outside the shell. Okay, now we will take out P outside the shell. See here, this is the Q, charge distributed on spherical shell. P is the point where electric field is to be calculated due to all these charges, and we will draw a Gaussian surface. Wait, this is the Gaussian surface, that is your spherical Gaussian surface which covers your spherical shell, and this is having the radius, this sphere is having radius small r. See here, this is small r, the radius of the sphere. Now again we will take a small surface element. See here, this is the small surface element, and this is area vector. ds is your area vector, that is the area vector drawn normal to this surface. Is it okay? Now that is you will take on a sphere, you will take a small surface and draw the draw your normal in outward direction, right? Imagine your this one tennis ball, and now see the electric field. This is your the direction of the electric field. Again the electric field and the ds both are going in the same direction, so the theta between angle between electric field and the area element, area vector, is equal to 0. Okay, now we'll apply the Gauss's theorem. See here, from Gauss's theorem, right, you know that E dot ds is equal to Q by epsilon naught, and this is also called your flux. Phi is also called your flux. And see here what happens now. Q is your what? First of all, you know that sigma is your what? Sigma is your Q by S, already discussed in last derivation, and Q will be equal to sigma X. One thing you clear it. Next is your regarding your ds. We wish to find electric field, so electric field will come out, and ds is your what? Surface integral over a closed surface. Now on which surface you want to find the electric field? On this point P we want to find the electric field, so we will take this surface. So for this surface, what would be your surface area? Since this is a sphere, so the surface area of the sphere is equal to 4 pi small r square. So we'll see this derivation how it goes on. Since E and ds are in the same direction, so what happens? EDS is equal to Q by epsilon naught, or E is surface. This is not required to write every time. You can write this one because we are finding the electric field, so not a flux. So electric field is take electric field outside, and ds is your integral of this surface. And this is the ds is your what, already discussed just now. Ds is your what, surface area of the sphere, that is equal to 4 pi r square. Small r is taken because we are taking the electric field here. We are measuring the electric field on this Gaussian surface at this point P. So its radius is your small r, so that we have taken 4 pi r square. And or E is equal to what? E becomes equal to 4 pi r square will come downward here, and E is equal to Q upon 4 pi epsilon naught r square is your relation. You can replace Q in terms of your what, sigma s also. In previous derivation we replaced Q by sigma s. Here also you can replace it by sigma s, but for derivations it is not necessary. Leave here. Don't don't confuse. Okay. Now let us take a next case. Leave it. I am not going to discuss. Now at a point on the surface of the shell, the case is your like this. This is your again the spherical shell having a capital R its radius, and now point P is lying on this surface. Okay, here in this case we have represented it by A. Now what is the Gauss's theorem? This is the small again surface element, this is the area element of this surface, and this is the electric field. Again the angle between E and ds is 0 degree, so we can apply the Gauss's theorem from Gauss's law. See here, this is Gauss's law. Now what would we write? We have to calculate electric field. So electric field will come out, and surface integral of ds will write. Surface integral of ds means your what? That is surface area of the sphere. Surface area of which sphere? This sphere. This is now carrying a radius r. So the surface area will be your 4 pi capital R square. See here what happens. E and ds are in the same direction. That is angle is 0 degree. So cos 0 is 1. Therefore E ds is equal to Q by epsilon naught. Next E surface integral of only ds, and E is equal, now what we will take, the surface integral of ds is taken as 4 pi capital R square. Now this 4 pi R square will shift here towards epsilon naught, and you will get the electric field. See, electric field is equal to Q upon 4 pi epsilon naught R square is your second case. The second case is when the point is lying on the shell. Now let us take the third case. Leave this one, I don't want to discuss. At a point B inside the shell. See the things. This is again your spherical shell, and now the point is taken inside the shell. Okay. Now the point is taken inside the shell. This is B point. Draw the Gaussian surface. This red is your Gaussian surface. See now what happens. According to Gauss's theorem, what is our Gauss's theorem? They have taken r dash as its radius, and surface element, area element, ds is area element of this Gaussian surface, and electric field is in outward direction. Okay. Now there is a thing from Gauss's law. You know that E dot ds is equal to Q by epsilon naught. Since this spherical shell is not bounding any charge, because what is our Gauss's theorem? That surface integral of electric field over a closed surface is equal to 1 by epsilon naught time charge enclosed in it. Enclosed, the charge should be enclosed in the Gaussian surface, but there is no charge enclosed in the Gaussian surface, so Q becomes equal to 0, and ds is actually 4 pi r dash square, but electric field will be finally 0 because Q is equal to 0. See the derivation, E and ds are in the same direction. Therefore what happens? EDS same as what we are doing in previous one. ds is equal to 4 pi r dash, so 4 pi r dash square. Okay, or E is equal to Q is taken as equal to 0, therefore E is equal to 0. So the electric, since Q is 0 inside the Gaussian surface, therefore what happens? E is 0. So inside this property E is equal to 0 inside a cavity is used for electrostatic shielding. That we'll discuss in next chapter. But the concept starts from here, that when you have a conducting spherical shell, the electric and charge is lying outside the shell on the surface, there is no charge inside the cavity. Okay, when you are having the hollow spherical sphere like tennis ball, in that case electric field is zero inside your what, inside a hollow or inside a cavity, and this is used for electrostatic shielding. This finishes your chapter, and I have already sent you the PDF regarding this chapter, and you can go through the derivations from there only.